Okay, let's get started. Last time we were talking about the earthquake, and we'll learn that the earthquake start in the fault. If you have a fault, the earthquake is going to start in the fault, and the start point is going to be the hypocenter or the focus. And as a result, energy is going to be released in a form of energy wave or seismic waves. And since it's a waves, we need to know how to measure the different types of waves that is going to be released from the earthquake. So those who are going to measure the different type of the seismic waves, it's the seismology. Seismology is a study of the earthquake waves. And we have the seismograph or seismometers. Those record the movement of the Earth in relation to stationary mass or constant mass. So we're going to have like a constant mass, which have a pen in order to record the movement, whether it's horizontal or vertical. On rotating drum, we call this rotating drum or magnetic tape. And the earthquake is going to cause vertical and horizontal ground movement. So we need to have like machines like this one here in order to measure the vertical and the horizontal movement. And since it could be vertical or horizontal, it means that we are going to have more than one type of seismograph in order to accurately record the movements. And also through that, we'll be able to describe the intensity of the shaking. Here, we are going to see seismograph in order to detect vertical movement. We say that the earthquake, it could cause vertical or horizontal movement. Here we are going to have a mass, and the mass is connected with a spring here. And when we are going to have vertical movement in the earth, what will happen? The mass here is going to move accordingly. And the mass here is connected with the pen recording. And here we have rotating drum. So when the earth moves up and down, the ball here is going to move accordingly. As a result, I'm going to have like a graph showing the change in the vertical movement. And when the earth moves up, the ball is going to move down. And when the earth moves down, the ball is going to move up. And I'm going to have a graph like this one. Also, I need to measure the horizontal movement. In that case, the ball is going to be connected with a wire here. And also, I'm going to have a hinge. So the hinge here is going to allow the movement in that direction. And when I'm going to have movement, side to side movement, to the left and to the right, then the ball here is going to move accordingly. And as a result, you are going to have a graph like this one. Show us the change in the horizontal movement. So this one, it will show us the change in the vertical movement, while this device is going to show us the change in the horizontal movement. And we know that when the earthquake is going to take place here in the fracture, and is going to start with the focus, hypocenter. And the energy is going to build up here. And when we have relative movement, the energy is going to release. And as a result, we are going to have seismic waves. And we need to measure these seismic waves. And we are going to classify the seismic waves into surface waves and body waves. If it's surface waves, it means that the movement is going to take place here at the surface. If it's body waves, it's going to take place here in the body of the Earth. So the seismic waves, it could be surface waves on the surface, or it could be body waves on the body of the Earth. Furthermore, we are going to classify the body waves. It could be primary waves, the P waves, or it could be secondary waves, the S waves. The surface waves, it could be R waves, and it could be L waves. R here stands for the Rayleigh. Rayleigh is the scientist who is the come up with a model to describe the R waves. L here stands for Love. Love is the name of a scientist, also responsible for making a model to describe the L waves. So let's start with the body waves. We say that the body waves, the waves that go through the body of the Earth. And we're going to start with the P waves, the primary waves. It's worth to mention that the primary waves is the fastest kind of seismic wave, very fast. And the first wave to arrive to a seismic station. So if you have seismic station, the first wave that is going to be recorded in the station is going to be the primary waves. And we need to describe how the primary wave is going to travel through the body. In order to understand this, we need to make experiment using slinky. Most of you are familiar with slinky. So this one in the picture here is a slinky. So if you have a slinky at rest, like this picture here, if you are going to push the slinky in that direction and release it, then you are going to see this part here is going to compress. And when you release this one, you are going to see that you are going to develop a wave which is going to move from that location to that location through compression and expansion. So you are going to notice that this part is going to compress and this part is going to expand. And after a time, then the wave is going to move in this direction. So this part is going to compress and this part is going to expand. And we need to know this one is the direction of the movement. If we are going to look at the body itself, when the time is 0, here we have the particle. We are going to have horizontal and vertical lines so that we can notice the change in the particle itself. So when the time is 0, we have nothing. And the y is going to be the direction of the wave or the propagation. When the time is 0, when the time is equal 1, here we are going to compress this part. As a result, this part is going to compress and that part is going to expand. So if you are going to make comparison with the original body, this one, the particle here is compressed, compare with this one. And the particle here is expand, compare with that one. When the time became 2, then what will happen? The wave is going to move again. And that part here is going to compress, compare with that one. And that particle here is going to expand, compare with that one. Until the wave is going to completely move from that point to that point. So here, the primary wave is going to move from one point to another using the compression and the expansion. And we say that the primary wave is very fast. Generally, in any solid material, P waves travel about 1.7 times faster than the S waves. Again, the body waves, it could be P or it could be S, primary or secondary. And the primary is 1.7 times faster than the S waves. So you can see here how the wave is going to move from that point to another. So the wave is going to start here. We are going to have compression, expansion, until the wave ends. The second type of the body wave is a secondary wave. Secondary waves move the rock particles up and down. So in order for that waves to move, is going to make up and down movement. And that best described by the rope here. If you have a rope at rest, like this one, when you shake this one, the rope is going to be up and down, like waves. So if this one is time 0, this one is going to be time 1, and this one is time 2. So the wave is going to move like that. You are going to have up and down movement. When the time equals 0, we have nothing. When time equals 1, we are going to have up and down movement. Then when the time equals 2, the up and down, it will move here. When the time equals 3, the up and down movement, it will move here. So this is how the secondary wave is going to move. Here in this picture, we can see how the secondary wave is going to move by up and down movement. So we have the primary, which move with the compression and expansion, and we have the secondary move with the up and down movement. Then we are going to move to different type of waves, the surface wave, the wave that is going to take place just below the Earth's surface. Seismic waves are somewhat similar to the surface wave on water. So this one is similar to the movement of the water. They cause the soil, they cause rocks and soil to be displaced in such a way that the ground surface ripples or undulates. It means that the surface is going to be like when the waves is going to move in the oceans. And we need to know that they have the lowest velocity, which means that the surface wave is going to come late behind the body waves. And also, they last to arrive at a recording station. They are the last one to arrive at a recording station. Also, they are going to cause the greatest property damage, mainly because they are going to take place on the surface of the Earth. And we say that the surface wave, it could be R waves. R stand for the relay, the name of physicist, the one who make the mathematical model for the R waves. And these one are when the surface wave that cause the ground to move up and down, similar to the movement of the ocean's swells or the ocean waves. So here we are going to see like wave movement, but this one is going to take place near the surface of the Earth. So the surface of the Earth is going to be like that. And the rock itself is going to move in circular rotation, anti-clockwise circular rotation. If this one is the wave direction, then the rocks beneath the Earth's surface is going to move like that. If you are going to put it in a model like this one, if this one is the reference model, when t equals 0, when t equals 1, the surface is going to be like that. When time equal to, when the wave is going to move from here to here, that part is going to be like that. And when the time equals 3 is going to be like that. This is how the wave is going to move from that point to that point. And the rock beneath the Earth is going to be like that. And here the model, the movement is going to be similar to the movement we see in the oceans, the surface of the oceans. The second type is the L waves. L stands for love, the name of seismologist. Actually, you could be, this one is mathematician, because he's the one who made mathematical model to prove the love waves. And this movement is going to be like snake movement. Actually, the ground is going to move side to side. So this one is going to move in this direction, and that part is going to move in this direction. This part is going to move in this direction, and that part is going to move in that direction. So the direction is going to be like when you are having a snake moving around. So here you can see the movement. It's just like a snake moving around. So this is the lava wave. Now, if I have the epicenter at that point, and I want to record the waves, like we mentioned, we have 4 types of waves. We have the body waves, and in the body waves, we have the primary waves and the secondary wave. And the surface wave, we have the R wave and the L wave. When an earthquake took place here, we know that the energy is going to be released in a form of seismic waves. So we are going to put a station here and here and here. So at station 1, the green light here is for the primary wave and secondary wave here, while the red one for the S wave here. So if you get the recording from station number 1, you are going to see in the recording machine, you are going to see the movement of the primary wave, and then you are going to see the movement of the secondary wave. So why I'm going to see the primary wave first? Because we mentioned that the primary wave is the fastest wave. Actually, it's going to be 1.7 more than the secondary wave. So at station 1, if we are going to say that the difference is about 5 minutes, 5 minutes between the P wave and S wave, at station number 2, where this difference is going to expand. So the time is going to be more than 5 minutes. And at station 3, the difference between them is going to expand more. So we are going to receive the waves at different interval times. And for humans, it's difficult to feel the P and S wave. Actually, it's going to be felt by animals. So if you are going to see a dog who making a strange movement, he's worried about something, it means that he have already heard the body waves, the P wave and the S wave. We can feel the surface waves. So now we need to know how to determine the size of the earthquake. In order to do that, we have 2 fundamentally different measurements. We can use the intensity of the earthquake, which means that we are going to observe the property damage. So when an earthquake hit a certain area, we are going to see how much property has been damaged. And based on that, I'm going to classify the earthquake. And we have a very famous one, which is Mercalli scale. This scale is based on the intensity. And we have the magnitude, another measurement. This depends on quantitative measurement of ground motion based on data from seismic records, used to estimate the amount of energy released at an earthquake source. So this one depends on the measurements, the vertical and horizontal measurement, and it's going also to be related about how much energy is going to be released. And the most famous one is the Richter scale. So the most famous method using the magnitude is the Richter scale. So a Richter scale is like a magnitude number. In that system, we have a certain number is going to be assigned to an earthquake on the base of the amount of ground displacement or shaking. So it depends on your measurement, the vertical and the horizontal measurement. We are going to come up with a number. Okay, we are going to come up with a number. So we call this the Richter number. And the movement is going to be near the epicenter. So here we have a graph. In the x-axis, we have the magnitude. It's from 1 to 10. And in y-axis, we have the maximum ground motion. So like you can see here, the curve here is not linear. Actually, the curve here is logarithmic scale, which means that if you are going to have an earthquake equal 7, so if the Richter scale measuring 7 here, it means that that scale would be 10 times larger than the scale of 6. So if you have a scale of 7, it's going to be 10 times larger than the scale of 6. Why? Because the measurements here, it depends on logarithmic scale. Okay, here the last figure, we can see the relation between the magnitude and the number of the earthquake per year. Relation with the energy release. So if this one logarithmic scale here, we have 1, 2, 3, 4, 5, 6. Here we can see the number of the earthquake per year. So for example, if the earthquake, the scale on the Richter scale is equal 3. That means through this year, we have witnessed about 100,000 earthquake. And here we can see the energy release. Energy release here equal 470 kilograms of explosive. Another example, if the earthquake here equals 6 on the scale of the Richter scale, it means that through the years we are going to see 100 earthquake. And here we can see that the energy, if I have a scale of 6 on Richter scale, that means I'm going to see an energy which is released equal to Hiroshima atomic bomb. Okay, so here we can see the energy released, and here we can see how many earthquake is going to take place through the years, and here is the Richter scale. Okay, so I'm going to finish here. I hope that you understand the lecture. I know it's difficult. It's not easy, but I think you can handle it. Okay, I'm going to stop here. The time is over. If you have any question, please be my guest.